Okay, 8th grade. So today we are looking at invisible fields for non-contact forces, if we can see them. Our Tennessee Science Standard is 8.PS2.2. That's to conduct an investigation, so we're going to have to do a little bit of investigating today. To provide evidence that fields exist between objects exerting forces on each other even though the objects are not in contact. Our objective is to define non-contact forces, and we're going to try to list the 4 different kinds of non-contact forces. Then we're going to provide evidence that fields do exist between objects exerting forces on each other, even though the objects do not come in contact. That's if we can provide that evidence. So we'll see if we can do our objectives for today. We've already discussed this in class, but we're going to go over it just as a refresher. This is what is force. Force is the push or pull experienced by an object when it interacts with another object, which results in the change of state, either from rest or from uniform motion. We have 2 different types of force. They're contact force and non-contact forces, and we've already done a little bit dealing with contact forces, where one object physically pushes or pulls another. And as you know, forces are measured in units of newtons, which is represented by a capital N. Our examples of contact forces is a reaction force, tension, friction, and air resistance. In our image of the baseball player, we can see him sliding into home plate. I'm assuming it's home plate. And there is friction working against him, as you can see represented by the arrow, the red arrow. Then we have our skydiver. Looks extremely happy to be jumping out of an airplane. Hopefully the parachute works. And air resistance is acting upon the skydiver that is physically touching the skydiver. Then we have our team that are in the green shirts here. Not sure if they're some type of a soccer team or a rugby team. And they are playing tug of war with this rope, and that is the tension that is acting on that. Now we have our non-contact forces, and this is going to be a 2-part discussion. We're going to start with our investigation today, and we're going to finish talking about this tomorrow. For our non-contact forces, we have one object pushing or pulling another without physically touching it, hence the name non-contact forces. There are 4 kinds of non-contact forces. We have gravity, which is an attractive force, meaning pulling only. Magnetism and electrostatic. Both of these are attractive or repulsive. They can be either one, which means they pull or push. Then we have a nuclear, which is an attractive force only. Newton's law of universal gravitation states, now these type of forces, we're just going to basically be able to list these and talk a little bit about them, but this is not what our main objective is for the day. So it states that every massive particle in the universe attracts every other massive particle with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Magnetism is the force exerted by magnets when they attract or repel each other. Magnetism is caused by the motion of electric charges. All magnets have north and south poles, as you can see in the image, and opposite poles attract, like poles repel. So for figure A and B in this image, you can see that because the same poles are facing each other, our arrows are going outward, meaning that they are repelling each other. For C and D, you can see that the opposite poles are together and the arrows are showing that they are attracting to each other. Electrostatic force is an attractive and repulsive force between particles caused that's due to their electric charge, so the electric force between stationary charged bodies is known as electrostatic force. This is also known as Coulomb's force, named after the French physicist Charles Coulomb. Now, for our nuclear force, we have 2 types of nuclear force. We have our strong nuclear force, and its main job is to hold together the subatomic particles of the nucleus, which is the protons that carry a positive charge and our neutrons that carry no charge. It's very short range, so the particles must be extremely close for the effects of the strong nuclear force to be felt. Our weak nuclear force governs the decay of unstable subatomic particles and initiates the nuclear fusion reaction that fuels the sun. But don't be fooled by the name. The weak nuclear force is actually stronger than gravity. So now we're going to get to our investigation. We're going to start by watching a video. Just basically, this person is playing around with magnets and a compass and some balls that are metallic and non-metallic, and we're going to see what happens when these magnets are placed close together. And the magnets are mainly the ones we're focusing on right now. So playing with two magnets, in this they're not labeled, but the red is facing the red, so we have two poles facing the same, and they're not physically touching, but yet one magnet is moving across the table. Now we have our attractive magnetic force. You can see that different poles are together here and they attracted just like magic. This person did not have to push one magnet toward the other, they just attracted to each other. And now they're going to take these balls and they're going to roll them down a ramp. One is going to continue in a straight path. As you can see, our non-metallic ball, and the metallic ball is going to sort of curve. So it is being affected by the magnet. But like before, the magnet did not physically touch that metallic ball. Now, the attractive magnetic force on this compass needle, as the person moves this magnet across the table without touching the compass, you can see that the magnet or the compass needle is moving. Now, when they flip the magnet around, you can see that the compass needle has moved differently. Okay, so we're going to start with our first experiment, and this is basically just a demonstration, but if we had been in class, this is something that we would have attempted to do. We're going to set up a magnetic field viewer. So basically this girl is putting a non-slip material here on the table. Then she's going to place a bar magnet on top of the non-slip material. Over top of that, but it's on legs, so it's not directly touching, she's got this tray, and she's going to sprinkle some iron filings all over the top of the tray. And you can see that the magnet's underneath. And once she taps, it causes the iron filings to sort of settle into place. And you can see somewhat of a pattern. Now, once the paper has been placed on top of this tray, meaning that the iron filings and the magnet are physically not touching each other, because the paper and the tray is separating them. Once she taps this paper, watch what happens to the iron filings. Take a good look. Now, for our second experiment, so that's working with magnets on those two experiments. This one is dealing with electric field patterns and electric charges. This one is a little bit of a longer video, which you're more than welcome to watch on your own, but I cut it just to this section right here. This is a petri dish, and they have two opposite charges, and they're sprinkling some semolina seeds over top castor oil, so that way it will lay on top of it and not sink down into the liquid, because castor oil is very thick. As you can see, there is something happening with the semolina seeds. But what exactly? Now, I know this is a little bit blurry and far out, but here in just a second they zoom in so you get a closer look. Okay, so from both of our videos and our first video of basically the magnets touching or not touching but being repelled or attracted to each other, what can we conclude? What can you conclude after watching the videos? Fields do exist between non-contact forces. You can get a better view of this with the magnets in the magnetic field demonstration. And then the electric field, you could see that there was fields that did exist from looking at the semolina seeds and the iron filings. Can you see field lines after the experiment that were not visible before? So in the first video where we have just the two magnets and the metallic and non-metallic ball and the compass, we could not see actual lines or anything connecting the two. But in both experiments, the lines were visible. Once the iron filings settled into place, you could see lines running from the north to the south pole. You could also see lines in the semolina seeds that were formed from the electric charges. So are the lines similar or different between the magnetic experiment and the electric experiment? Explain your answer. Take a second to think about this. The lines are similar. Because the field lines travel in a pattern from the North Pole to the South Pole, and in the experiments it was either opposite poles or opposite charges, opposites attract and like repel. So yes, there were field lines and there's fields that do exist. A field is a region in space where an object with certain properties will experience a force. Scientists use a field to explain how one object can affect another without physically touching it, such as our non-contact forces, even without any substance between the objects. And in the magnets, at the first video, you could see that the magnets were not physically touching each other. Just want to make sure that you see that even though they're not physically touching, there is field surrounding them. With fields, it's better to talk in terms of attraction and repulsion rather than push or pull. There are 3 examples we experience in everyday life. Now, these are the 3 that we're going to talk about tomorrow to continue our discussion on the fields that exist. Gravitational field. The Earth is surrounded by a gravitational field that pulls all objects to its center. A magnetic field. A magnet is surrounded by a magnetic field which pushes or pulls other magnets and things made of iron, nickel, and cobalt that are located within it. And the electric field. A charged object is surrounded by an electric field which exerts electrical forces on other things within the field. So, for our assignments, we are going to research non-contact forces. I want you to make sure to cite which source that you used and find 3 examples of non-contact forces in everyday life. This is fairly simple. Just a simple internet search will get you these 3 examples. You may want to find some that are a little bit more difficult research. That way yours is not the same as everybody else's, but if it is, that's fine. I'm just asking for 3 examples of non-contact forces in everyday life. Then I'm wanting you to research gravitational fields and magnetic fields and electric fields. You can pick one of these to research or you can pick all 3. But I do want you to look up some articles about these. You don't have to actually do an assignment on this. This is just your research assignment because we're going to talk about this tomorrow and I want you to be able to participate. Use the first simulation link to draw a bar magnet and show how the lines run from the North Pole to the South Pole, and don't forget your arrows. So the first simulation link down here says magnets and electromagnets. You're going to play around with a bar magnet. And you can see that there'll be different things that you can select on the side to help you draw your lines and show which way the arrows would be pointing. Okay, and these will be the lines like we've seen in the magnet or both experiments, but you could really see it with the iron filings about how those run from opposite poles or like poles. Then you're going to use the second simulation link to play electric field hockey. You must make 4 goals. This can be a little tricky. I tried this myself and it took me quite a while to get just 1 goal. I want you to try to make 4 goals. And for each goal that you do, you use a different strategy. You're going to take pictures of each goal that you make. That way I can see what strategy you used. And you're going to put it in a Word document for me to look at. I'm going to be grading these. So you need 4 goals. Okay. You can make these a little bit more difficult by putting up walls or things like that, and you can play around with it and stuff if you like a challenge. If not, you just simply have to make 4 goals, take a picture of each, and put it in a Word document to submit. And that is your assignments for today. If you have any questions, feel free to ask. Then we'll go into a deeper discussion tomorrow about the different types of fields. Have a good evening, guys.